this second question, we're looking at calculating the volume of a gas. Now, interestingly, there's actually a lot of information in this question that we don't need. Although at the same time, we could use it depending on how we decide to solve this question. Since the number of moles isn't changing, we could solve this as a combined gas law and compare the conditions on Earth, our standard temperature and pressure, to the conditions on Pluto. Alternatively, we could solve this as an ideal gas law problem, and that's the way I'm going to approach it here. So PV equals nRT. We're looking for volume, so volume is equal to nRT over P. Now I'm going to start filling in the terms. So the volume is equal to the number of moles, which is given to us as 1 mole, times the ideal gas constant, which you can find on the front page of the exam, liters atmospheres over moles Kelvin. So our first two terms were pretty easy to plug in, but the temperature we have is negative 220 degrees Celsius. The ideal gas law, especially with the constant we're using here, requires that we be in Kelvin. So to get to Kelvin, we take our degrees Celsius and add 273.15. So we get 53.15 Kelvin. Then we divide this by the pressure. Pressure here is given in pascals. So our value for R that we're using is in atmospheres. So we're going to have to convert from pascals to atmospheres. Easiest way to do that is first convert to kilopascals. So 1 kilopascal is 1,000 pascals. And then 101.3 kilopascals is 1 atmosphere. And so we get 9.86 times 10 to the minus 6 atmospheres. And we can plug that in here for P. When we calculate this out, we're going to calculate this given the measurement of 1 mole up here was one significant figure. That's what we need to keep here. And so by taking that 1 mole of oxygen, which took up 22.4 liters, and taking it to Pluto, it now occupies a volume of 400,000 liters.